Hello, welcome back to JK Chemistry. Okay. Today we are going to discuss about most important fundamentals in organic chemistry. So firstly, we just to go through the all effects, that is electronic effects in organic chemistry. So first of all, we just list out those electronic effects in organic chemistry. The most important one is resonance effect or mesomeric effect. We will discuss later. Okay, so it can be plus R effect or minus R effect. So resonance effect or mesomeric effect. Some rare another kind of resonance effect is called dancing resonance effect, and aromaticity. It's also it exhibits some kind of resonance effect. That's why I just listed in this category. Next important electronic effect is that hyperconjugation, followed by inductive effect. It can be plus I effect, minus effect. Then electromeric effect. It can be plus E effect, minus E effect. In this video, we mainly discuss about resonance effect or mesomeric effect. We can analog this resonance effect with the simple pendulum or oscillatory motion. We know if you have a stationary simple pendulum, you just apply a force. It can move towards this direction. It can move this direction. That means it execute a to and from motion. It moves this way. Okay. Some textbook or some kind of literature, or you can see this kind of overall motion of this pendulum just like this. This can be this position, this position, this position, like this. Okay, they are represented like this manner. That means this is the hybrid of this oscillation. Hybrid of this oscillation. They are represented. That means this moved this way. Okay. Okay, so we can analog resonance effect like this. Okay, so, clear. Okay, now we move our topic, that is only just like a model. So in order to study anything in science, we want to obey a model, so it would be better to learn. Okay, see this molecule. So this molecule having lone pair electron, this is our oxygen, right, having a negative charge. Okay, ready. Same way, you just listen this molecule. Okay, this molecules having oxygen and carrying negative charge. What is the difference between these two? This negative charge is localized. It can't move anywhere. Okay, so it is permanently at this position. Negative charge at this position. That means it is localized electron. This is localized charge. What about this? This is not localized. This is called delocalized charge. That means that charge or that excess electron can move from here to there, here to there. So this is basically called conjugation. This is basically called conjugation. Okay, so this is a localized charge. This is called delocalized charge. So we in our previous lecture we have mentioned any molecule having any charge, it will be somewhat less stable compared to its uncharged condition. So that's why it is very angry. That means highly reactive. This is highly reactive compared to this oxygen. This oxygen is highly reactive compared to this oxygen. Why? Here this charge is localized, here it is delocalized. That is, this charge is not much available at this position. It moves somewhere else. Okay, but this charge is always there, always there. So that is the concept in organic chemistry. Localized charge will be more reactive compared to delocalized charge. That is, localized charge is always available compared to delocalized charge. Now we move into our resonance concept. So you just analog our this concept. So this analog with this position. Okay, now here we know that 6 electrons. Okay, one of the pair of electron can move from this oxygen to this OC bond. This OC bond, what will happen? We already mentioned that when we draw a curly arrow having two head or doubly barbed arrow, what means a pair of electron moving and it will be going to make a bond. That means you assume that whenever you draw this arrow to this bond, that means there will be a bond generation happen. So we know that carbon having only 4 valency. Earlier it has 1 2 3 4 valency satisfied. Now you moved this electron and you are going to generate another bond here that will exceed its valency to 5. Now naturally what should do, one of the bond should break from here. Okay, so you can have 3 chances: this bond, this bond, this bond. So you always remember that pi bond is weaker than that of sigma bond. So whenever you have a double bond or triple bond, you can have pi bond. Okay, so pi bond is more susceptible to breakage. Okay, so shift at that time this pi bond move on to this oxygen. So okay, so you can have another structure. Initially lone pair here, pi bond here. So when you shift this lone pair to this bond, what will happen? You can have a pi bond here. Okay, pi bond here, and pi bond is move on to this oxygen. That means this bond get migrated to oxygen. Okay, having negative charge. Okay, so again this lone pair can move to this position simultaneously. This pi bond move on to oxygen. It will move back to this position. That's why I analog with this kind of motion. Okay, it is to and fro motion. Same way it is a to and fro motion. Okay, it is moved to this position, again this move to position. As our pendulum hybrid, it can have also hybrid. What here we pictured its path of motion. Here we should picture the path of electronic motion. So electron is moved through this position. Initially pi bond here and finally pi bond here. That means this a pair of electron is moving between these two oxygen. That's why we represent hybrid as this way. Okay, so that is electron is this 2 electron is available for this oxygen as well as this oxygen. Okay, this is hybrid. And in resonance, generally we represent a resonance when we have a situation at which we can't draw the structure of molecule by means of single Lewis structure. At that time we want to draw many structures. Such a phenomenon is called a resonance. Okay, and we can draw a hybrid. Hybrid means that is somewhat stable structure of that resonance phenomena. Okay, compared to canonical structure. This is called canonical 1, this is canonical 2. Okay, so when we are comparing this localized and this delocalized situation, localized is very reactive. Okay, but I am happy, that means it is somewhat stable. Okay, so resonance effect is a stabilizing phenomena. Resonance effect is a stabilizing phenomena. Okay, we will discuss deeply resonance. I just introduced resonance effect here. Okay, so what are the situation you can expect resonance? Okay, suppose you have alternate single and double bond. Okay, that is conjugated system. At that situation you can expect resonance effect. So here double bond, single bond, double bond. What will happen? This pi bond move to this position. So what will happen? Valency of this carbon exceed. So at that time this pi bond move on to this carbon. So you can have a new pi bond at this position and its valency, one of the valency lost. Okay, so here it can have positive charge. Here a pair of electron moved, that means a pair of electron having a negative charge. So the negative charge means one electron is excess. That means this pi bond, one of the electron corresponds to this carbon, other electron corresponds to this carbon. So this carbon getting one electron excess. Okay, this is one situation. Another situation, if you have a carbonyl functional group and next group having a lone pair electron, at that position you should expect a resonance effect. At that situation you should expect a resonance effect. Okay, so this can have oxygen, nitrogen, sulfur. So any element having lone pair electron. So this lone pair electron move to this position. Carbonyl pi bond move on to carbonyl pi bond move on to oxygen. Okay, so you will end up with this canonical form. Okay, so lone pair shift, that means this atom having a deficiency of electron, that's why it's positive charge. This pi bond move on to oxygen, that means it can have excess electron, one electron. Again this move, you can get back the initial structure. So this condition having resonance situation. Okay, another situation, if you have a carbonyl function group and you can have it is just analog to this conjugated system, alternate double and single bond. So here we represent double bond, single bond, double bond. So instead of this double bond, I just put carbonyl functional group. So in this situation also you can expect resonance. So how it is, pi bond shift this position, at that time pi bond move on to oxygen, right? So positive charge, negative charge. Then again lone pair move to this OC bond and this move on to this CC bond. You can get back your initial structure. Okay, so these are the fundamentals. So when you are able to draw this resonance structure, you are good in organic chemistry with reasonable arrow. Some students, they are trying to by heart this resonance. It is very dangerous. You can't by heart this resonance. If you have a single concept, an idea, you need not memorize. You just understand. That's why I just analoged with this kind of our oscillation, pendulum oscillation. Okay, it is just like that. Okay, and another question, among CH3CO2 minus and HSO4 minus, which one is more stable? Okay, so it is based on resonance effect. We already we have drawn a resonance structure of, this is a carboxylate acetate ion. Okay, so acetate ion. Okay, so it is a resonance structure like this, we already drawn. Okay, so this is CH3, C double bond O minus. So shift, you will end up with this structure. So you can get back the initial structure by this type of movement. So you will end up with this hybrid structure. So these two oxygen partitioned this one negative charge, two oxygen partitioned one negative charge. What about sulfate ion? Okay, we can draw the sulfate ion structure. So this is our sulfate ion. So what will happen? So this one of the lone pair electron can move to this position and this pi bond can move to this oxygen. So you will end up with the next canonical form, OH already here new bond. Okay, and here you can have a negative charge with the excess one electron. Okay, here double bond. Okay, ready. Now what will happen? This lone pair electron can move to this position and pi bond can move to this position. Okay, so you can have another canonical form, double bond O, OH, double bond O minus. Okay, so when we are comparing these two structures, you can see the one negative charge is here, it is distributed among 3 oxygen, but here one negative charge distributed among 2 oxygen. So the canonical form will be, the resonance hybrid will be so pi bond distribution here also, pi bond distribution here also, pi bond distribution here also, delta minus, delta minus, delta minus. So resonance hybrid is like this. So here the one negative charge is distributed between 3 oxygen, here only 2 oxygen. So among CH3CO2 minus and HSO4 minus, HSO4 minus is more stable than CH3CO2. So from this we can clearly understand that this resonance effect can be utilized to explain the stability of several concepts. Okay, clear? So in the next video we will discuss a different type of resonance effect. Okay, so subscribe, like, share. Thank you, take care.